Hello, everyone. My name is Wilfredo Robinson, and today I will be presenting our paper, Spatial Audio Enhanced Multimodal Graph Rendering for Efficient Data Trend Learning on Touchscreen Devices. My co-authors are Medhani Kalal, Jennifer Tennison, and Jenna Gorlewicz from St. Louis University, and Nicholas Giudice from the University of Maine. Now, digital graphs are everywhere, all shapes and sizes, all manner of topics in all kinds of devices. Now imagine trying to extract information from them when you cannot see them. That is the challenge that people with blindness and low vision have to face every single day. So how do they currently address these issues? Well, with physical formats, we have embossed printouts, thermoform, and swell paper, like the map of Alaska example that we have on the left, pin arrays and refreshable braille displays, like the example that we have in the middle of the screen. These tactile formats, they give very rich tactile information, but they usually come at a high cost. You need assistance or trained personnel, and you need time to render the graphs in these formats. So with digital formats, we have mostly screen readers like JAWS and NVDA, and mobile assistants and screen readers like iOS VoiceOver and Android TalkBack. With these, they are portable, sometimes more affordable, but the richness of information that you find in a graph or in an image is sometimes difficult or limiting to express through alt text or audio descriptions alone. So, what other research teams are trying to do to enrich this digital experience is, for example, Ramlo and colleagues focused on large 2D tabular data. They are trying to add sonification to the exploration of this tabular data. Wall and Brewster, they show a graph on the desktop, but then instead of exploring it with the keyboard, you explore it with a special tactile mouse and a tactile tablet with a stylus. And finally, more recently, Zhang and colleagues have focused exclusively on screen readers and on providing intuitive drill down techniques and feedback schemes such that the person can load the graph into the screen reader and start off at the most general of layers with just the summary of the graph, and then use gestures to drill down and increase granularity until they reach the individual data point level. So what our research team is trying to do is to reach a middle point by using touchscreens. Touchscreens are very powerful accessibility devices because they can naturally present information in three modalities: visual with the screen, audio with the speakers, and haptics through the use of vibration motors. We are looking for ways to keep the interactivity and finger exploration of physical formats, but use them on a digital device. To showcase how these graphs and shapes can be explored on a touchscreen, I will use our group's work from 2020, which was a user study with individuals with blindness and low vision, where they had to explore bar charts and shapes. For the bar charts, their finger would be freely moving across the screen. Whenever they reach a label or a number, it would be read out to them through text-to-speech. Whenever they reach a bar, the device would start vibrating, and when they reach a bar of a different category, the frequency of the vibration would then be different. For shapes, whenever they are on empty space, there is no feedback. Whenever they touch a side of the shape, there is strong vibration. Inside the shape, there is no vibration, but a subtle continuous audio cue to differentiate empty space inside and outside the shape. Whenever an angle or a length is touched, it will be read out to the user, and right angles and corners were also sonified to notify the user of their presence. It is important to note that these multimodal feedback schemes are the results of over a decade of work from this group and of answering different questions to get to this point. For example, Tennison and colleagues in 2018 asked the question, is a bigger screen always better? The answer is no, bigger is not always better. In 2020, Polanyi and colleagues asked the question, if you have multiple vibrotactile lines, how thick do they have to be, and what is the gap that has to exist between them to make them distinguishable from each other when the user is exploring on the screen? Pasquesi and Gorlewicz in 2021 then asked, if we're going to use vibrations, then which vibrations are detectable by the user, and then which vibrations are distinguishable from each other by the user. This group has also proposed rendering guidelines for these graphs and shapes in touchscreens. Now, however, the team faced an interesting challenge because as graphs get more complex and they have hundreds, thousands, or millions of data points, and they can have any shape like heat maps or scatter plots like the ones on screen, what's important now is not identifying the individual bars or individual data points, but identifying the general shape of the graph, the general trend of the data. So how can we give the user more information about their localization on screen relative to the screen and other elements on it without overloading them with additional modalities? Well, one potential solution comes not from adding more modalities, but from tweaking one of the existing modalities. That is where spatial audio comes in. Spatial audio has been used in other fields of research, typically to aid users in locating themselves in an environment. For example, Vasquez Alvarez and their group created a navigation system based on landmarks and audio cues that aided users in navigating through structures in real life. Spatial audio helped users locate themselves better in this real life environment. Loomis had a similar experience in 1998 when they were guiding users through a virtual environment. They also noticed that spatial audio made the tasks easier. And more recently, Yang and their group were training a neural network to interpret the video content that they were showing it. And they noticed that if they added additional dimensions so that the neural network could understand not only what audio was coming out from the video, but where it was coming from, the interpretation performance of what was actually going on screen would increase. Noticing this pattern, we decided to integrate spatial audio into our multimodal feedback scheme. I'll explain it with the histogram and the scatter plot on the screen. You're exploring the graph with your finger. It starts vibrating. You found a data point or a bin. How to tell where that point or bin is without any numerical data? With audio. The audio feedback for that point will come from the left speaker only, telling you that the point you found is on the left side of the screen, and the pitch will be a high pitch, telling you that it is on the left top side of the screen. Now you found the point on the bottom right. The audio cue will come from the right speaker only with a low pitch. And if you found one that it's in the middle, you would have the sound will come from both speakers and it will have a neutral pitch. Now, to study the influence of spatial audio more in detail, we have 3 research questions. Number 1 is, how does spatial audio affect the extraction of data-related features from the graph? Number 2, how does spatial audio affect the extraction of physical features of the graph, such as the size, the orientation, etc.? And 3, would users prefer to use spatial audio in their free finger exploration of histograms and scatter plots over non-spatial audio renderings? Now, to try and answer these questions, we carried out a pilot study last year with 5 participants with blind and low vision, ages 16 to 22, and we spent 60 minutes with each participant. Those 60 minutes were split in 2, 30 minutes for training and 30 minutes for testing. During the training phase, they would have to explore simple histograms and scatter plots in an embossed physical format and then on the touchscreen, and they would have to answer comprehension questions. Once answered correctly, they would pass on to the testing phase where they would have to explore 2 histograms and 2 scatter plots. They would have 2 minutes to explore each of these graphs freely with their own strategy on the touchscreen, and then they would have 2 additional minutes to recreate the graph from memory. Not to answer numerical questions about the graph, but to recreate the graph and see if they could recreate the shape of the graph and the general trend of the data using Wikisticks. Finally, after all the graphs were done, we spent 10 to 15 minutes openly discussing with the participant about their experience with these multimodal feedback schemes. For data collection and analysis, the tablets would log across time the finger location data on the screen while the participant was exploring. We took pictures of each of the recreations that participants made with Wikisticks, And we also took videos of their hands while they were exploring the touchscreen and then recreating the graph from memory. We then judged these recreations based on 4 criteria. Number one, did the recreation account for all the inflection points in the original graph? Number two, did the recreation include all of the modes of the histogram and their correct location on the screen? For the scatter plots, both sides of the curve and where it properly connected. Number three, what is the orientation of the recreation with respect to the original graph on the touchscreen? And number four, the size of the recreation versus the size of the original graph on the touchscreen. All of these were rated from 0 to 4, with 4 being the best score. Before getting into the numbers and the results, it is important to remember that this was a 5-participant pilot study where participants had limited time to explore and recreate these graphs. So we limited our quantitative analysis to descriptive statistics and our qualitative analysis to describing the strategies that participants used, which will be shown later on. To answer the first research question, how does spatial audio affect the extraction of data-related features, which are inflection points and trend? Well, we can see that participants performed either the same or 3 to 9% better when exploring with spatial audio versus without, which means that spatial audio has the potential to positively aid users when extracting data-related insights. And as for the second question, how does spatial audio affect the extraction of physical features, in our case, orientation and scale? Orientation, it's a mixed bag, but for scale, participants consistently performed worse when exploring with spatial audio versus without, which means that spatial audio has the potential to alter the mental image that the participant forms in their mind of the graph. Whether this is a pro or a con will depend on future work. As for participant strategies when exploring histograms, in these graphs, darker points are earlier in the exploration time, lighter points are later in the exploration time. Some participants would start on the bottom left, then start tracing right, find the bin, trace it to the top, then move right, find the other one, trace it to the top, and so on until they reach the right, then go all the way back to the left and do it again until time ran out, while other participants, like the one on the right, would start on the left, then do the same process until they reach the right edge of the screen, and then instead of going to the left, they would start backtracking from right to left. With scatter plots, something similar happened, where on the left, it shows that some participants would start at the top, start scanning left and right while moving vertically downwards, and the image on the right shows that some participants would start on the left, start scanning up and down while moving to the right of the screen. One participant used 2 fingers when exploring scatter plots. They would move one finger until they found the point, anchor that finger there, and then use their other finger to find other data points, anchor the finger when it found another one, and continue this process until the whole graph was scanned. Finally, as for the participant preferences, all participants agreed that scatter plots were more difficult to explore. One of them said, "The frustration is looking for or identifying the dot. It takes a while to pinpoint where it is." 4 out of 5 participants preferred spatial audio when exploring histograms, and that one participant that did not said, "It's easier for me to determine the pattern of the histogram without spatial audio." And finally, all participants preferred spatial audio for exploring scatter plots. One of them used an example from their education. If a teacher gave you information, like a number, then based on its value, I can find it near the bottom or near the top. I think functionally, the different pitches are helpful. Finally, for future work, firstly, we aim to address some of the hardware limitations that these devices have, such as only one vibration motor, by looking for ways to give feedback, independent feedback to all fingers on the hand with one single screen. We aim to produce multimodal feedback schemes for more complex scatter plots and some other complex graphs like box plots. And finally, we aim to provide ways in which there exists a two-way communication between the device and the user when exploring these graphs. I will end by mentioning that this work is supported by the National Science Foundation under multiple grants, and that any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation. Thank you very much.